Okay, now that we have had some time to think about root locus and how to construct it, let's think about how we can use it to implement a better controller on our system. Let's imagine a system where we have just a standard second order system. Let's do 1 over s plus 1, s plus 5 on this. And let's just put a simple proportional control. So what we have here is a K and a G, our G, and our feedback element in here. And let's look at the root locus for that. Well, what we can see is that we've got two poles, one here at -1 and one at -5. And if we drew the root locus for this, I'm not going to go through the details on this, but it's going to look like this. Okay, we've got two branches going to infinity, and so in looking at this, we can know that as we increase the gain, we're from 0 to infinity. We're going to start with an overdamped system. Dominated fairly heavily by the pole at -1, and as we increase the gain, they're going to move together to be critically damped at the -3 point, and that's the fastest we can get it without having any overshoot for a second order system. And then as we increase the gain a little bit faster or a little bit higher, we're going to pick up some oscillation in the system. So we really are fairly limited with this. We can improve the performance and by increasing the gain to a certain level, but then we're kind of stuck. So what we really want to do is end up down here, further down here, where we know it's faster because we move on the negative real axis. We increase faster, and we like to stay close to the real axis to minimize the oscillation. So what we'd really like to do is bend these guys around, bend those branches around and get them reattached to the real axis. And so knowing what we know now about this, what we can do is drop a 0 in here in our controller. Okay, and the way that's going to work in our controller is we're going to end up with something that looks like this. We're going to still have our KP, our proportional control, just like we have, but in this case, now we're going to put a KD and an S in there. That's our integrator, and we're going to sum these two together, and then we're going to drive our plant with that, and then have, of course, our feedback element in here. And so now what we've done is created a PD controller, and so if we place that 0 that gets created there out here, now if we look at the root locus, we're still going to have this on the real axis between the -1 and the -5, but now this one's going to go out like this. Now, in this case, we have one branch going to infinity, which is the branch that's going to the -180. So where are these two branches going to go now? Well, one of them is going to go to -180, and one of them is going to go to this 0. So the branches have to come back in here like this. They have to exit here, and they have to come back in. So what's going to happen is this is going to loop around like this in order to satisfy all the requirements. Now, what we've done in this case is we've satisfied what we wanted to do. We reshaped the locus to bring these branches on around here like this, and we can operate in here in this range where we're faster and have lower oscillations in them. Now, the 0 adds a little bit of a change to our system. We no longer have a true second order system. We've got a second order system with an additional 0. So it isn't truly critically damped anymore. We're going to pick up a little oscillation because this integrator term in here, the derivative term in there is going to reshape that step input before it gets to our plant. and so it's going to be a little different. But the principle still holds the same. And so let's jump over here to MATLAB and see what MATLAB will tell us about this. Now I've created just a small little script in here that will create a second order system, just like we've talked about, a pole at -1 and a pole at -5. And I've run that to create a G variable. And then I put that G variable in here in CISO tool, which you're learning about in lab this week. And then let's pop over to CISO tool. There we go. And see what CISO tool is doing for us. So CISO tool, I've got it set up so that it shows us the root locus and then the step response. And we can see our open loop poles here and here at -1 and -5. And then our root locus is shown here in the blue lines. And it's showing exactly like we sketched it. Now the pink dots are our closed loop poles. And so when we take them to 0 or reduce our gain, they will be at the open loop poles. And what we end up down here is a very slow system as we anticipated. We've got a settling time of around 5 seconds in here. A fairly first order-ish kind of response. A little tweak here at the start due to this pole here at -5. But as we grab these closed loop poles, increasing the gain and bring them to critically damped here at -3, what we see is a improvement in the speed. Now we have a settling time of about 3 in here, but we still, that's about as good as we can get. If we grab onto these poles and try to move them, let's see if I can get them to move. Yeah, there we go. Move off axis, we start picking up oscillation. And if we move them even further off axis, there we go. We get even more oscillation, and so at some point it becomes unmanageable. We're getting too much overshoot and too much oscillation in our transient response for this system. So now let's come in here and let's add a 0 to this. So I'm going to grab a 0 here from my root locus editor, and I'm going to drop it on here, and then I'm going to go to my controller. There we go. My compensator, and I'm going to select this. I'm going to put this, I dropped it just at -4, and I'm going to put it in here at -10. I'm going to move it around and get it to reshape that. I don't need the compensator anymore. And so now we see the root locus did exactly what we anticipated. We've still got the 2 poles here, 2 open loop poles, and now we've added an open loop 0 by adding that 0 to our system. And if we take our closed loop poles back down to 0 again, we still get the same kind of response. We're still fairly slow out here, 4 or 5-ish. But as we start increasing the gain, we move these to where they're critically damped again. And we're about the same. We're still about 2 seconds in here as the settling time. Now, but let's look and see now as we increase the gain even further, what we do is we can move it up here, and what we end up doing is picking up some oscillation in here. A little bit of oscillation because we're moving it off axis. But if we continue to go with this, what we can do then is move it over here to where it's critically damped on the other side of the circle. And what we see now is that our settling time is more like 0.3. We've reduced the settling time by a factor of 10 in this by adding that 0 in here. And so this is called a PD controller. Okay, and the derivative term actually improves the transient dynamic effect. We can make the system faster by adding this 0 in there. And it allows us to reshape that root locus to get us to do what we want it to do. Now, we could push this 0 on out here even further, and we could improve the performance even more. We could push this gain on here, increase the gain and push it out here, and now look, we've got a settling time of like 0.15. We could push it out, we could push it out, we could increase it, and in theory that works just fine. In practical terms, it has limitations, because as you push this out, you're going to run into high frequency stuff out here at some point. Something's going to start moving around that you didn't expect and you didn't model, and it's going to start showing up in your response. And so we want to push it as far as we need to, and then probably settle for that. We could try pushing it further if we have a real piece of hardware and don't mind tearing it up if we push it too far. But at some point, we are going to run into some high frequency stuff, and it's going to limit how fast we can move this. So anyway, that's taking a look at the PD controller in the root locus environment, and allows us to speed up the system by adding that derivative term in there. All right.